So as we go to our deepest level of fluid dynamics, we're going to hit the fundamental concepts here. And the two concepts are the conservation of mass and the conservation of momentum. We're going to apply them to a couple different type of control volumes, the result of which is going to give us either the conservation of mass and momentum in integral form or the conservation of mass and momentum in differential form. This video is all about conservation of mass for a finite control volume, which gives us the integral form of the equation. And so here's what we want to do. First and foremost, realize that a conservation law is a concept. And we're going to write an equation for it, but what that is the mathematical representation of an idea. What idea? Well, the idea that mass is neither created nor destroyed. If that's true, then the rate of change of the conserved quantity, i.e. the rate of change of the mass in the system, has to be equal to interactions that increase it minus the rate of the interactions that decrease it. And so we have that the rate of change of mass in a system is equal to the net flow rate of mass into the system minus the net flow rate of mass out of the system. Think for a minute, these two terms could just be combined into one single idea, which is the net rate of flow into the system, which would be all of the ones that go in minus all the ones that go out. That gives us a single number, which we could call the net flow rate into the system. So what I want to do is apply those two ideas and some building blocks that we've seen. For example, the mass in a system could be written in differential form, dm, as rho d volume. And the flow rate, differential mass flow rate, dm dot, can be written as rho v dA. If we take those two ideas and apply them here where we need actually the rate of change, where we end up is here. So let's dissect this term a little bit, or this equation a little bit, to see what we want. This is one of the four most important equations in the course. All right, so let's start with this left-hand term, in particular, this triple integral of rho dV. Well, you know what that is. If you integrate rho dV, that gives you mass. So this is just the mass in the system. And so you could have some cube and you could integrate from x, y's, and z's to get the total mass. Except we put this on front of it, this time derivative, and so this is the derivative of the mass in the system with respect to time. In other words, this is the rate at which the mass is changing. So if you were filling a bucket up, it's the rate at which the bucket would be filling up or draining or whatever. Okay, this term, this looks a little weird. Ignoring the vector math for just a minute, what you're looking at is rho v dA. In other words, a little differential m dot that's been integrated, and if we integrate both sides, it's just m dot, right? Rho v a. That's what this looks like. So this is a mass flow term. But what this v dot n business has to do with is that if we have a control volume like so, and maybe we have flow going in this end and out this end, there is some A1 and some A2, maybe V1 and V2. And these things are vectors. In this area, we can write a normal vector associated with that area. Normal vectors always point out, so we could call this n hat 1. And this area has one as well that we could call n hat 2. And the question is, how much of this velocity contributes to the mass flow rate? Well, the way I've drawn them here where they're all parallel, the answer is all of it. But if it were at an angle, things would get more interesting. And so all this dot product is doing is handling the fact that if instead V1, let's just get rid of this real quick. If instead V1 looked like this, where it has a x component v1x and a, say, y component, let's get a little coordinate system here of x and y, called v1y, only the x component actually contributes to the mass flow crossing this boundary. And so just a little bit of vector math to remind you here. Okay, these two are in the same direction, so v2 dotted with n hat 2 is just equal to the magnitude of v2, right? It's all there. But here on the left one, v1 dot n hat 1, well, they're opposite directions and we only want the x component, and so this is actually going to be equal to minus v1x. I'm going to show you a little bit more about how these dot products work, but it's best to just do it with examples. So you're about to get lots of example videos out of me, and the point here is that we're just going to move through these equations systematically and figure out how to handle each term and make them do something useful for us.